SwayamPrabha. Digital India. Educated India.
Okay, yesterday we have been discussing about design of non-catalytic gas solid reactors, and we again went to my diagram, that is kinetics, contacting, input, output and all that. So then we have also discussed what kind of contacting patterns you will get, right, depending on the type of reactor you are taking. That means if it is a blast furnace, rotary kiln, fluidized bed, moving bed, all various reactors what you have for non-catalytic reactions. And the precursor for that was that we should know the kinetics first, okay, and I hope you know the kinetics till now. I think what we are talking about is non-catalytic gas solid reaction kinetics. Okay, to summarize, I will give the equations which can be or which have to be used for the design. So the kinetic expressions what we have are kinetic equations for gas solid non-catalytic, I will write again NC, non-catalytic reactions. So you know, if it is only film control, I think anyway for 3 control you have the big equation and that has to be used at the end, but individually if I write, if I have film control, what you have is equation tau, T equal to rho b r 3b kg cag xb. This is the one which I asked you to derive. So tau is rho b r 3b kg cag. We know this equation comes when xb equal to 1, and T by tau is xb. This is very nice, simplest equation, T by tau. Good. So now if I have diffusion control, ash diffusion control, number 2, you should remember this, otherwise in the examination you will have the problem. Okay. So T alone, individual steps, rho b r square 6 b cag d. So this is only slightly complicated, 3 1 minus x b to the power of 2 by 3, 2 into 1 minus x b, right? Yeah. This is the equation. This equation is 4 and tau is rho b r square 6 b cag d. So this is equation number 5. Then T by tau equal to 1 3 x b to the power of 2 by 3, 2 into 1 minus x b. So this is the equation. This is equation number 6. There is a meaning why I am writing all this. Okay, then you have 3 reaction control. So here T equal to rho b r, yeah, b cag ks into 1 minus x b to the power of 1 by 3. This is 7. Tau equal to rho b r b CAGKS. This is equation number 8. Now, T by tau for reaction control is 1 minus xb to the power of 1 by 3. This is equation number 9, and all this is for constant size particle, right? Okay, constant size particle. Of course, here you can also list out there, just leave a space and then you can list out all 3 controlling. That equation also you can just leave it there. I am not writing that. And now, if you have changing size, if I say that this one has A, B, changing size particle, that means during the reaction size of the particle continuously changes. And here we have for film control, you have T equal to rho B R B kg naught CAG into 1 minus xb to the power of n plus 1 by 3 divided by n plus 1. This is equation number 10. So, tau is rho B R B kg naught CAG n plus 1. This is equation number 11. Then T by tau equal to 1 minus xb to the power of n plus 1 by 3. Correct, no? Yeah, this is 12. I hope you know the value of n for small particles, large particles. N varies from half to 1, okay, depending on the whether you have size small particle and large particle. And next one is the reaction control. For reaction control, T by tau is given by equation equation 9, T by tau. Okay. For reaction control, T by tau is equation 9. You do not have to repeat again. So, these are the equations you should remember for the design, because this is the kinetic models, right. So, which will give you the relationship between x b and T by tau or T, because tau also you know. Good. Yeah. So, once I have this, then the next one is contacting, right, contacting. And yesterday we have discussed about contacting, saying that whether you have blast furnace, the flow through that for both the phases are plug flow. If you have rotary kiln, again both phases move in plug flow. And if you have fluidized bed, then solids may move in mixed flow and gas may move. That is slightly difficult to find out, and when we are doing fluidized bed reactors, then you will know exactly what kind of pattern you will have, that I will tell you later. But to start with, if you want to assume, you can assume when you are near minimum fluidization velocity, it will be almost plug flow, right. I mean, there are people who can assume even the mixed flow for gas also, but that must be at very high velocities of gas. You know, in fluidization there is the minimum velocity that is required for fluidizing the particles, to keeping the particles in suspension, right. And there are very high gas velocities where almost terminal velocities are reached. So, if you reach terminal velocity, it is no more a fluidized bed, it is a transport bed, you know, all the particles will go out. Okay. So, that limit and all those things we will discuss that later. And if you have a moving bed means you take a cylindrical tube, maybe 1 foot diameter, and the height may be 20 feet, 30 feet, 40 feet, and you may send, for example, your iron ore slowly from the top, right, and from the bottom you may send your hydrogen or CO. So, then this will react, gas will react with the solid, and you should have sufficient conditions for the reaction to take place. Then what kind of contacting pattern you can take for plug flow, for moving bed? Both are plug flow, okay, because the moving bed you are allowing such that you fill up the entire column as a packed bed and then just remove the some small hole with a control of the wall. So, that fixes the actual flow rate from the top and bottom. Then the entire bed will be slowly moving down, that is why we call it as moving bed reactor. So, that is why any reactor you take, we can always break into our basic contacting patterns, whether mixed flow or plug flow. So, once we do that, then we should also think one more thing, we should also take one more thing into account. This I have mentioned in the beginning, as usual I think you may not remember. I told you that our most important phase is solids in non-catalytic reactions in many cases, okay. Almost 99% of the time we are more worried about what is the conversion in the solids rather than what is the conversion in the gas phase. So, that is the reason why solids are our important phase, and once you have solids as important phase, then we have to treat the solids as what is called macrofluid. I do not know whether you have, okay, I will write here macrofluid. Okay. And that is why the knowledge in reactor theory is also important here. If you have forgotten what is macrofluid and how do you get an equation for macrofluid, all that, then it may be slightly difficult for you, but I will just try to give the brief connection there. Okay. Good. And I have also given you the formula sheet for reactor design, some time back in the class earlier. So, there also for macrofluid, what is the equation and how did you derive that? That is very important here. So, conceptually what we are thinking is that one of the problems with RTD is that it cannot solve or it cannot give complete information to calculate conversions, and RTD can give the information only for first order reactions. Why? Because first order reactions conversion depends on the time, and RTD gives you that kind of information. So, direct combination there. So, RTD gives me the time. What is the definition of RTD? The time taken by the fraction of material which is coming between time t and t plus delta t. So, if I look at my reactor and if I want to find out what is the fraction of material that is coming between 10th minute and 11th minute, right. So, that fraction is Et dt, where Et is the excited distribution function and dt is the time interval, that is the fraction. So, now if I can add all those fractions, then I will know that the total amount of material, how much time it took, then I can take the average of that, then I will take the mean residence time or average residence time, all that you can get from RTD. But if I take other than first orders in second order, okay, there is one more parameter which comes into picture, that is called mixing, whether the mixing has taken place early or mixing has taken place late. And one of the beautiful examples that was given for this to demonstrate is this. I have a plug flow reactor, then followed by mixed flow reactor, and just reverse the same thing. Yeah, these are the two models, right. So, this is ideal plug flow, ideal mixed flow, right. So, I have this system, two systems, and if I conduct a first order reaction whether here or here, I get the same conversion, right. And if I conduct the second order reaction, this will give me more conversion and this will give me less conversion. So, the idea here is that here in the second order reaction, we have to keep the concentration as high as possible, because we have Kca square as the rate. So, if Ca is large, then you will have more and more more rate of reaction and then more conversions correspondingly. Okay. So, that is what is happening. That means, you should not allow mixing for higher order reactions greater than 1. Okay. You should not allow in the beginning itself. So, that means, you should delay the mixing as much as possible. Delay the mixing, here it is delayed. First I have plug flow, where by definition there is no mixing, we are talking about action mixing. Okay. Good. So, whereas here if I conduct the same second order reaction, it gives me low conversion, because here at the first instant itself you have the concentration decreased because of perfect mixing. The idea here is, when fresh concentration Ca0 is just put inside, then this will mix with, already there is a continuous flow, continuously reaction is taking place. So, this fresh Ca0 is mixed with already converted stream within the reactor, where the concentration falls, right. Product has a different concentration in the outlet, or here it is same concentration. So, that is why it now gives a low conversion here, and orders other than less than 1, this will give you more conversion and this will give you less conversion. It can be proved, and you can derive on your own. It is not great E equal to mc square type concepts here, it is very simple. So, that is why you can derive on your own and then try to find out. So, that is why now the question came here, that okay, you are telling about this is late mixing and this is early mixing. Okay, this is late mixing and this is early mixing. Can you say how late it is or how early it is? Because early and late are only relative terms, I think they are loose terms. General English only we will use that, but you have to be very precise in engineering to say that late means how many days late, how many hours late. So, that is why we cannot get that kind of information in these two systems, right. So, that is why we imagine a fluid where if I have broken up all my fluid, which is continuously going inside in terms of packets, where these packets are not allowed to coalesce or allowed to break. I hope you know what is meaning coalescence and breaking, of course, okay. Yeah. So, we should not allow, that means, once the packet enters as a packet, it comes just like that outside. Okay. This we call it as segregated fluid, okay. Or we can also call this one as macro fluid. And the other extreme is the microfluid, where we have individual molecules freely moving throughout the reactor. So, that means, any molecule, if there is a chance for reaction, any molecule can react with any molecule, because there is perfect mixing. In this, perfect mixing is possible in microfluid. You should not get confused here, but even this microfluid, there are two restrictions: the status of the fluid itself. Fluid can easily move in the form of individual molecules. That means, there is a possibility for the molecules to interact with any molecule in microfluid, right. But that is one restriction. The other restriction is that, suppose I put that in a plug flow reactor, these individual molecules microfluid, now I put in plug flow reactor, but by definition plug flow reactor is not mixed reactor. You are not allowing, I mean the molecules are capable of moving, but your system will not allow the molecules to move. That is why even microfluid behaves as macrofluid there. Okay. So, in a plug flow, whether I have microfluid, whether I have macrofluid or microfluid, it does not matter for me, because the treatment is same. What we see is every particle is entering and exactly leaving at the outlet, okay, with the same time, whether it is packets or whether they are individual molecules. So, the residence time is fixed for the packets, that is macrofluid, or for the individual molecules, and the reaction is taking place when it is slowly moving, and that is why we say that we have infinite concentration across the cross section. Okay. I mean not infinite concentration, infinite mixing. So, that means infinite mixing idea is here, at any cross section if I look, my concentration is same, but that concentration is varying with the axial direction. Okay. So, now good. So, as far as these individual molecules are concerned, we have understood now. Okay. If these individual molecules we are able to put in mixed flow reactor, they are capable of easily mixing. So, actually it will get diluted. So, that is why you get also less conversions. Now, how do you put this same information with macro fluid? I will now take these pockets of molecules and then pack here and continuously I feed and then they come out. Now, even in the packets the concentration is uniform, because if I look, all the packets will be exactly moving like this, exactly moving like that. So, then I can find out all the concentration here is same, concentration here is same, concentration here is same, within that line. So, again it is easy for me to imagine for plug flow, but if I put this same packets here in the mixed flow reactor, then by definition the residence time distribution, that means molecules coming from the start to end, it is 0 to infinity. That means some molecules may stay almost 0 time and some molecules may stay infinite time, that is molecules wise. Even if you take packets, some packets may stay 0 time, some packets may stay infinite time, and each packet now you can imagine as a small batch reactors. They are not allowed to mix with any other packet, right. So, that is why the reaction that is going on is only limited to that packet alone, right. So, now the concentration or conversion in that packet depends on how much time it has spent inside the reactor. So, some may spend only 5 minutes, some may spend 50 minutes, some may spend only 5 seconds. So, in 5 seconds packet the conversion is almost 0, let us say very small, or 5 minutes you will have some corresponding conversion, or 50 minutes almost the conversion would have been completed, conversion should have been 1. So, that is the reason why the average of all that is the one which you see outside. And I can also tell you like a story, like a story only I am now trying to tell you. So, now we can tell that if I have macro fluid, and if I have second order reaction, macro fluid, mixed flow reactor. Remember 3 conditions: mixed flow reactor, second order reaction, macro fluid. And the other case is again mixed flow reactor. Now, not microfluid, not macrofluid, microfluid and second order reaction. Which one will give you more conversion? Kavya, you are telling something? Why?
Because though they are being mixed, they are still in the form of.
Yeah. So, what is happening? Correct. Answer is right.
It is retained by each.
Yeah. Excellent. Excellent. Concentration is retained by that packet as high as possible. So, that is why you will get more conversion when compared to microfluid, right. I think this is the general information. I think this you have to remember all this. I say it is a wonderful concept, and remember this, which will make everything clear. So, that means if you put first PFR and then MFR and reverse it, and you will see that here you have more conversions for second order, here you will have less conversions for second order, and then the reason you have to question why that is happening. That is happening because that is late mixing, this is early mixing for second order reactions. So, then everything falls, because I cannot define, even now we do not have complete picture in reaction engineering, how to get that information we are asking. That means one extreme only you are discussing, that means you are allowing only packets in one case and all individual molecules in other case, but in reality you may have some packets and some molecules individually. Then under those conditions, how do you do that? Many people tried wonderfully and there are very nice models and all that, but still we are not perfect in trying to get the conversion in a chemical reactor. Now, what is the connection between this what I told, and also now the design in non-catalytic reactors, right. I told you that our important phase in most of the time non-catalytic reactions is solids. Would you take solids as microfluid or macrofluid? Yeah, if I take iron ore particle of, let us say, maybe 1 centimeter, then inside that we have so many molecules of Fe3O4, right. So, that one is like that. You can imagine all the particles are as macrofluid, right. So, once you have that macrofluid, Now, how do you find out the conversion for this macro fluid? Even here, if I have this, I told you that imagine that only we have mixed flow reactor, the other one also we can imagine, but this will give you slightly more information. Then continuously I am putting the packets and continuously they are coming out under steady state conditions, but when I am concentrating at time t equal to 0, let us say 100 particles, 100 macro fluid packets, I just put it there, then out of that one may come out, right, immediately. Then afterwards maybe 5 minutes, 10 minutes, all that you may come out. Now, what you are trying to do at the end, you have to average the concentrations of all these packets within that batch what you focused. So, like that continuously, anytime you imagine, that is what is happening. Continuously I am feeding the packets, continuously they are coming out, but depending on their own residence time, you will have the conversions, and all that average conversion is what I see at the outlet. Okay. So, imagination here is that all those packets have been broken into molecules and then try to find out what is the conversion there. So, then that is what we see, but actually what is happening is each individual packet will have a different conversion, you are averaging that all that. So, that means what is that mechanism, what is happening there? I have, let us say, between maybe 5 minutes to 5th minute to 6th minute, how many packets have come, what is the conversion in that. Okay. How do I get the information between information on 5th minute and 6th minute? How do I know how many packets are coming? Do you have information or you do not have information? Question is clear, or I am just asking, I want to find out in any reactor, anyway here I think mixed flow we are talking. So, what is the what number of packets are coming between 5th minute and 6th minute? Do you have that information? RTD, instead of packets, instead of fraction I said packets, that is all. So, RTD will give you between any two times what is the fraction of material that is coming out. And now the kinetics, if you have first order or second order, that kinetics will tell you now what is the conversion in those packets, right. So, between 5th minute and 6th minute, I have 100 packets, or the fraction may be 10% of the material. Okay. So, within that what is the conversion, and that conversion is dictated by kinetics. So, that is why kinetics and contacting, this RTD is nothing but contacting, right. And if I take ideal mixed flow reactor, I have a specific RTD, right, because mixed flow I am telling. So, when I have mixed flow specific reactor, then I know definitely my RTD, the reverse is not possible. That is also a wonderful point which we have discussed last time. So, that means given a reactor, you know definitely what is the RTD. Okay. Here if I give you, I have a mixed flow reactor, then you know the equation is E t equal to e power minus t by t bar by t bar, that is the equation what you have, right. But if I give you this equation and then ask you what is the contacting pattern, you can generate infinite number of possibilities are there. This is again wonderful point, I think you have to remember. Okay. We have discussed that in the last semester. So, you understood the question, no? I think it is very nice. Given a reactor, you know definitely what is RTD, but given a RTD function, RTD equation, you can never say what kind of reactor you have. But only one possibility, one condition is that if you have plug flow direct delta function, no other system can give you direct delta function. Direct delta function is the RTD for plug flow. No other system can give you that direct delta function except plug flow. But whereas with mixed flow there are many possibilities. There is nothing new or totally weird thing what we are discussing, because it is already been discussed by Leonspiel for long time in his book. Okay. All other books also, right. But Leonspiel gives that beautifully. So, that is why I think you have to read once more all this information. Okay. So, that is why when you go for actual writing the equations, then we need these kinetics, because this is what gives me what is the conversion that is going on in each and every packet. This one, all these equations, depending on film control, depending on ash diffusion control or reaction control, or depending on 3 controlling, that is also right. That will give me in those packets what is the conversion, and my ET dt will give me what kind of reactor, we have. Okay. So, based on that only we have derived that equation for segregated fluid. Okay. Design expression for macro fluid. Okay. Here we have the macro fluid for solids. Yeah, we have 1 minus x bar b equal to 0 to infinity 1 minus x b of single particle into E t dt. So, this is equation 13. So, this is the equation. I have written this in slightly different form than what I have given in the that formula sheet. Okay. So, actually what is this one here? Yeah, C A bar by C A naught, and this is C A bar by C A by C A by C A naught batch. Okay. Here it is single particle. Now, you can see if I have this E t dt for plug flow reactor. So, then this becomes Dirac delta function. If I have mixed flow ideal reactor, so then again you have here E by e power minus t by t bar by t bar. So, those things you have to just substitute there, and it is not only ideal reactors, any non ideal reactor also this is true. Yesterday Satyam was asking me, sir, in a blast furnace where if you do not have ideal plug flow, what do you do? If I do not have ideal plug flow, what is the nearest non ideality that comes for plug flow? Axial dispersion. We have an equation for E t dt or E t for axial dispersion, that is what you substitute here. If I do not have ideal mixed flow reactor, then we have a mixed flow reactor with dead space, because mixing is not perfect, and that happens many times in fluidized bed also, because some part of the bed is not that vigorously mixing, that vigorously fluidizing, and some other part in the bed because in industry you will have 3 meters 4 meter diameter fluidized beds. Okay. 4 meters is I think maybe 3/4 of this room, that is the diameters what you have. So, some part it may be very active, some part may not be active because of non uniform distribution of gas. So, that is why you have dead spaces there. So, you also have a model for E t if I have dead space and bypass. Okay. So, that is why you have all that information, and I also gave you last semester that you have so many models also, possible combination of models for E t dt, for residence time distribution models. I also gave a handout there at that time. So, that is why all that information can be used in this equation, right. Okay. So, normally what happens here is that when I put 0 to infinity as the upper limit, is it really realistic, or do we have to change that value physically? What do you mean by infinite time? What will be x b for infinite time? Yeah. So, that entire integration disappears. So, then what is the logical upper boundary? Excellent, tau. Tau is the logical upper boundary. So, this equation is 1 minus x bar b, this you write first, then this is 0 to tau. See, beyond tau you do not have x b equal to 1. So, that function disappears. Okay? Yeah. So, that is why you have to put only this maximum is tau, this is single particle E t dt. This is the actual equation. Yeah. And of course, now if I have this E t for ideal plug flow or ideal mixture flow, now I can substitute and then get the values. Okay. This is the general expression for, yeah, I think I will actually write maybe tomorrow all these things, the actual equations we write for plug flow as well as mixed flow reactor. And what I would like to tell is, here this x b is not an easy function except for this, correct? No, this x b is simply 1 minus, I can add 1 minus 1 minus x b. Okay. So, this 1 by, see this equation, yeah, I think I do not know whether you have realized that or not, E t dt is in terms of time, and x b also have to convert in terms of time. So, that is the relationship what I have been telling you, you need the conversion time relationship for kinetic model, from kinetic models. So, that is why this equation gives me that relationship, 1 minus x b now expressed in terms of t time, tau is constant anyway, that those things I know how to calculate. So, that equation you have to substitute here. If it is film control, here I have to substitute 1 minus t by tau here, and then here I know if it is a packet bed or I mean plug flow, or if it is ideal mixed flow, then I can integrate that equation. Integration is not easy, I think it is normally complicated equations only you get. Okay, now you see diffusion as diffusion control. Yeah, so this is the equation which I have to solve first. I have to get from this equation 4 1 minus x b. That 1 minus x b should be expressed in terms of t or t by tau. Okay, this equation, equation 6. This is easy instead of writing all that things. So, t by tau. So, this x b 1 minus x b has to be solved and then substitute there and integrate. So, this is a cubic equation now, and then it is not that easy. And even here the other one, yeah, here, yeah, this is easier, yeah, this is easier than this. Okay. So, that is why I have written all these equations in this fashion, so that you will have immediate relationship between this design expression and then that. This is the final design expression. What do you get from this? If I give you time, maybe this yeah, we have in terms of time here, right. If time is, let us say 20 minutes, 30 minutes, 40 minutes, what is the conversion? Okay. Or of course, if you substitute after the integration these limits, that will be in terms of t by t bar, t bar by tau. Tau is associated with individual particles. Please remember that tau is associated with individual particle. T bar is associated with reactor. T bar is associated with reactor. Yeah, I think maybe you did not catch my point. Here, if E t, if I write as e power minus t by t bar by t bar, this is, let me say clearly, m, right. So, this t will disappear because it is a definite integral, okay, this t, small t, then you will have in terms of t bar m and tau. Huh? Oh yeah, minus is there, yes. Yeah, okay. So, that is what. So, you will have the equation only in terms of t bar and tau, tau we know anyway, okay, that is no problem. Now, given x bar b, calculate t bar. T bar is associated with, again I am telling you, the average residence time of the particles. How do you calculate? Volume by volumetric flow rate, right. But in this case, it is not volume by volumetric flow rate, it is hold up by W is hold up kgs by F, what we call kg per time. So, t bar I know now. Okay. So, we have to find out this t bar if x bar is known. If t bar is given to you, I will say that okay, I have so much they hold up inside the reactor, and I know what is F, the flow rate, that is actually your input, F is your input here. Okay. So, then I can calculate t bar. Using that t bar, I can now calculate what will be the x bar. Given is the same thing, same design. If you know the volume, calculate conversion. If you know conversion, calculate volume. You cannot do anything if you do not know both. if you do not know either this or that. Okay, at least one you should assume, one you should know. Okay. So, I think we will stop here.